Okay, we're going to do an energy equation dealing with springs and their stored energy. Uh, so, there's a lot of information in this problem. We'll start off reading it. Uh, in a pinball machine, a knob is pulled back in order to launch a solid metal sphere. If you don't know what a pinball machine is, you should probably look it up. If you have never seen one or you don't know what we're talking about, this problem's a little difficult to envision, so I kind of looked up for a picture, and this is essentially what we're looking at, this setup here. Here's your solid metal sphere with some mass. And that mass, it turns out, is 50 kilograms. So that sphere has a mass of 50, excuse me, not kilograms, grams. But we do want to convert that to kilograms, so the mass is actually 0.05 kilograms. And this thing has a radius of 15 millimeters. Now you may be thinking to yourself, why are they giving me this information? Why do I care what the radius of this thing is? Can't I just figure out what the spring is and determine how fast this thing's going to go uh, shooting out? Well, we're going to have to deal with some rotational kinetic energy here. So that's why they're giving us the radius. So we've got the radius of the ball, and that's equal to 15 millimeters, otherwise known as 0.015 meters. We know the knob on the spring is pulled back with a force of 50 newtons. So we know there's this axial force of 50 newtons pulling it back. So you got this force of 50 newtons. And it compresses this spring 0.25 meters. So essentially the displacement of the spring. So normally the spring's out here, while it's at its equilibrium point, and it's pulled back 0.25 meters. So that's how far the spring is displaced. And we want to know with what speed the ball will be traveling when the spring reaches equilibrium and it's no longer in contact with the solid sphere. Uh, that's not really worded correctly. Uh, so we want to know the speed of the solid sphere, the ball, when the spring reaches equilibrium and yeah, okay, that is worded correctly. And it's no longer in contact with the solid sphere. So when the spring reaches equilibrium, how fast is the ball traveling? This is an energy balance equation, so essentially our potential energy is going to be equal to kinetic energy. Our potential energy initial is going to be equal to our total kinetic energy final. Uh, so I rewrote this. Let's back up before we just jump into that equation that I was going to write down. And let's say that all the total energy initial, potential and kinetic, equals all the potential energy and total energy, all the total energy final, potential, kinetic. That's our conservation of energy. And we're going to assume there's no losses in this problem. Uh, so what is our total potential energy made up of? Well, if we use this as our kind of point of reference for gravitational energy, gravitational potential energy, then the gravitational potential energy just drops out and we don't even have to worry about it. Meaning we're only left with potential energy elastic initial elastic potential energy. And because this thing is going to reach equilibrium, the elastic potential energy in the final stage, because this is reaching equilibrium in the final spot, is going to be 0. So this whole potential energy term just cancels out, and it's 0. And initially, the kinetic energy total is 0 because the ball's not moving, okay? And the spring is still storing energy, is not moving either. So the total kinetic energy initial is equal to 0. This one's 0, and this one's 0. And you're left with your elastic potential energy initial is going to equal your total kinetic energy final, which is made up of kinetic energy translational, linear, final, plus the kinetic energy rotational final. So if we expand these equations, we know that the potential energy elastic is equal to our elastic constant times the displacement squared over 2. Now, we don't know what this is. This is not given in the problem. So we're probably going to have to find it using the force and displacement. But let's try and derive the equation for this final velocity. Let's try and derive this equation for final velocity. Because some things might cancel out, we might have to do less problem solving. So if we start reducing this down and isolate VF as our only variable on one side of the equation, what we would be doing first is we could multiply everything by 2, multiply everything by 2 to cancel out the 2's and get everything out of fraction form. The other thing we know is that I is the solid sphere, the ball, has a moment of inertia equal to 2/5 mr squared. So I, for the solid sphere, is equal to 2/5 mr squared. And we can plug that in. The other thing we can plug in is the fact that omega, angular speed, is equal to v over r for radius of the sphere. First thing we can probably notice is that our r is going to cancel out. This is just going to be vf squared times r over r squared. R's are going to cancel out, okay? And if r's cancel out, we're left with the following equation. The next thing that we can do is we can see that we have a like term here, vf squared. We can add these together. We can add these together by saying that this is 10, this is 5 over 5, not 10, 5 over 5 mv squared, and add these two fractions together. You're just adding fractions and like terms. And you're left on the right side of the equation with 7 mv f squared all over 5, and that's equal to k times delta x squared. Excuse me, I'm going to back up. You're left with k x squared equals 7 mvf squared over 5. Again, this is all derived from the energy. We're just manipulating the letters and seeing what we can cancel out so we don't have to worry about. One thing we need to do is take care of what k equals. So we have the Hooke's law, which is force. Let me do it a different color. Force equals the k constant times the displacement. Okay, k constant times the displacement. So our k constant is equal to your force over your displacement. And if we take that, and plug that in over here, when we plug the the K constant is equal to, plug this in, we'll see that one of your displacements cancels out, and you're left with force times displacement is equal to 7/5 mvf. And rearranging our formula, we get Vf equals the square root of 5 times the force times the displacement over 7 times the mass. And we have the force, displacement, and the mass from up here. Force, displacement, and the mass. We plug in all our values to solve for Vf. When you plug in all your numbers, you will solve and find that Vf is equal to 13.4 meters per second. That's 13.4 meters per second. Just backing up, you could go through and solve this problem by just, plugging in your numbers, what you have for displacement, what you have for mass. Same thing over here. You could solve for your moment of inertia and solve for your omega, plug in the numbers, figure out what the K constant is, and plug in the numbers all up here, and go through the process of doing algebra as well. I like to do the process of deriving a formula for the situation, which is derived right here, and solving using that. I tend to make less errors when I do this. I tend to make less calculating errors when I do this.